Hey everyone, welcome back to the channel. So in today's video, we're going to discuss 5 important system design algorithms that are quite important if you are preparing for a system design interview. So we'll be discussing those algorithms with code examples and we'll be using multiple type of models available there to implement them. So without wasting much time, let's get started. Have you ever thought of like when you use some application like Uber or Rapido or Ola, how they're able to find the nearest driver for you in just a mere of seconds, right? So there are like two important concepts of system designing. So basically geohashing and quadrant trees. So that's what we're going to discuss about today with examples, and we'll see how these two techniques enables these ride hailing platforms to leverage this technology and find the nearest driver for you in the quickest way possible. Okay. So first, let's just start with the concept number one of geohashing. Okay. So what does geohashing means? There are two terms involved in it, right? Geo, then hash. So basically, what does it mean? Geo means the globe. What we do in geohashing, we divide the entire globe into some blocks of hashes. Okay, some hash values. So if you see this image here, which I've taken by the way from Geeks for Kicks. So in geohashing, what do? We divide the region, okay, into let's say multiple blocks. Okay, let's say here we first divided and if you see there is a India map here, okay, in the background. So what we divide it, let's say, into 4 quadrants. Then each division we can further subdivide it, okay. And if you see the prefixes that are there, the prefix of parent division is inherited to the child divisions, and then we append 0, 1, 2, 3 like this, right? Then again, if you want to, let's say, further subdivide 1, 3 into 4 more blocks, we can do this way. So this is how we convert the entire geographical map into blocks like this, and each block is given a hash value, right? It's a hash value. Don't worry, we will see an example in the end of this video, like how to convert a given latitude and longitude into a hash value like this. So I'll explain the logic. We will be using a concept called binary encoding there. I'll explain you there. But for now, let's just understand in the high level view. So if you can see here, we have just shown 3 divisions, okay? But are 3 divisions enough? I mean 3 subdivisions like this? No, not really, right? If you see in block number 230, Kerala lies. Kerala somewhere falls in this 230 block number. So it doesn't. You cannot have just one block like this, right? If someone from Kerala is looking for a ride in, let's say, Rapido or Ola, you just cannot go and search the entire Kerala state, right? So we have to further subdivide it. So what we can do, we can further subdivide 230 into 230. 0, 231, 232, 233 like this. Then again we can further subdivide each of those subdivisions. So like this, how much you want to subdivide, that depends on your app and services that you are designing. Let's say you can define some rule like until each block is covering at least 3 or 4 kilometers of radius, okay, or let's say 20 or 30 degrees of latitude movement. You can define thresholds and rules like this for your application. Until it covers that threshold or that limit, you will keep on subdividing it. Now once you have done that, this entire geohashing is stored in a database. So it became like a static hash data for the entire geographical map of our globe. So once this is done, then comes the next crucial part. Okay, now let me just extract a portion of this geohash. Let's say I take this, okay, and I'll just import it here, okay. Here you can see there are 4-5 states that are coming in these 4 blocks, but let's just assume that this is what a map of let's say Kormangla looks like, right? Kormangla, Bengaluru looks like, okay. Just assume for the time being. We could have subdivided it into further strings, but that string will become lengthier, so I don't want to do that. Yeah, before jumping to this, let me just discuss one more point, okay. So if you see the prefix that we are generating, the numbers or the hash values that we are generating for the children blocks, if you see the neighboring blocks will have similar prefix. If you see the block number 133 here, right, 133 has 4 neighboring blocks here which share the similar prefix of 1 3 which have been inherited from its parent. So that's what the beauty of geohashing is. So longer the shared prefix between two geohashes, the spatially closer they are together, right? That means if you see 132 and 133 are spatially closer. I mean in the space they are closer because they share a common prefix. But 133 and 303 are not spatially closer, right? Because they do not share a common prefix at all. So that's how this geohashing is important. Now let's jump to this example, okay? Now let's say the geohash map for Kormangala, Bangalore looks like this, okay? And let's say this is the entire Kormangala area in Bangalore, which have been divided into 4 quadrants like this, okay? Now let's say you are a rider, okay? Let me just see if I have some icon for this. Okay, let's say you are a rider, all right, and you are searching for a cab or a taxi or a bike in Rapido app, okay? Now you will have your own latitude and longitude, okay, where you are staying currently. And let's say when we convert this latitude and longitude into geohash, so we'll basically pass this into a geohashing algorithm. As I told, I'll explain this in detail with an example in the end of the video, okay? And let's say you passed in the latitude and longitude for this and it generated a hash value or geohash value of 213 for you, okay? That means you as a user are actually falling in this quadrant, okay? So you are let's say here, all right? Now what will happen? Now once your geohash value is determined by the application using its own geohashing algorithm. So now what it will do? Now this is where the second concept which we are discussing in the beginning of the video, quadrant-tree or quad-tree comes into picture, okay? Now what quad-tree will do? It will first identify that you as a user are located in the geohash value of 213. So in this block you are located, right, in this quadrant. So what it will do? It will first try to fetch the nearest available riders, okay? Don't have taxi or something like that. Let me just import it from somewhere. Let's say we have multiple taxis available like this, okay? Let's say we have taxis available like this in this quadrant, all right? Now what this quadrant tree or quad tree algorithm will try to do? Now what is a quadrant tree algorithm? It's basically divides a given two-dimensional space. So this is a two-dimensional space, right? So quad tree, what it will do? It will basically divide it given two-dimensional space into 4 equally spaced quadrants. So it will further subdivide it, okay? If we further subdivide it, now before subdividing, first what it will try to find out whether we have some taxi or some target points. So here target points are taxi drivers, right, or the taxis. So whether the quad tree in the current quadrant, if it has some target elements or not, or taxis or not. If it has, what it will do? It will then try to narrow down the search space, okay? See, one thing it could have done, once it determined that yes, we have some taxi in this quadrant, okay, in this main quadrant, first quadrant, or in this 2D space, what it could have done? It could have simply, calculated a distance between your location and the taxi's location for each individual taxis, then whichever is closest, right? So whichever is the closest, let's say this is the closest, it would simply assign you that taxi for you to ride, right? But ideally it doesn't do that, okay? Because we can always, if we have options to optimize the things, why not to do that, right? So what it will do? It will further subdivide it into 4 equally spaced quadrant, okay? That's why it is a quad tree. That means 4 sub trees or 4 branches it is creating, 4 quadrants it is creating for a given quadrant, right? So what it will do, let's say it will divide it. Let me just change the color a bit to black. So so it divided this two-dimensional space into 4 equally spaced quadrant, right? Now out of this, now it will, what it will try to do, it will then again figure out in which quadrant. Let's say the 4 subquadrant that has been generated are A, B, C and D. So let's say this is A, B, C and D. Okay, in clockwise manner I am typing A, B, C and D. Now if you see, the user is located in quadrant C, right? So the first priority, the quadrant tree algorithm will give it to subquadrant C. What it will do, it will first try to search for drivers or taxis in this quadrant. That means because you are located in subquadrant C, it will try to fetch drivers in this location. Now it will find that it is not able to, right? Because here you see there are no drivers available. Then what it will do, because C was discarded, because it could not find C driver in quadrant C, we are left with A, B and D. Then what it will do, it will look for the nearest quadrant. So there are 2 nearest quadrants, B and D, right? Because we moved in clockwise, A, B, C and D. So B and D are available. So it will then try to search in these 2 quadrants. Okay. Now you see that in quadrant B we have a driver, and quadrant D also we have a driver. So we have 2 options left right now, right? The algorithm has 2 options to choose now. Now what it will do for each taxi, okay? Now for each taxi, it will then, it has its own latitude and longitude, right? Because taxi are present, right, in a physical location. It will have latitude and longitude. Now for each taxi, it will calculate the geohash. Okay. It will calculate the geohash for each of them. Let's say geohash value for this is, the first taxi is, let's say 213001 or 112, something like this. And for this taxi it is, let's say 21300304. okay. Now using these geohash values, what it will do, it will then try to calculate the distance, the closest available taxi for your location. It will then try to calculate the distance for these 2 taxi and then assign you a taxi driver for you. Okay. Let's say it did not find any taxi at all. Okay. Or let's say, let's discuss the other way around. Let's say it again found, let's say, multiple drivers here, right? Okay. In this space. So what it could do, it could recursively again divide it into 4 more subquadrants, okay, to narrow down the search more, right? It could have done that, and it does that actually. How does quadtrees work actually? They recursively divide a given physical 2D space until they reach at a point where the target points are available. So now you might think, how deep it will go, how much recursively it will go on dividing the quadrants. It cannot go to an infinite level, right? There again, it becomes the requirement of your application. So what you can define, you can define threshold and rules for your application, that if a quadrant has more than 5 drivers or 10 drivers, right? Let's say 10 is the threshold. So if a quadrant has more than 10 drivers, subdivide it into four parts. Okay. So you can define thresholds like this so that you can narrow down the search space. Okay. And then find the nearest driver as fast as possible. So that's how the quadrant tree algorithm works. Okay, along with geohashing, to fetch you the nearest available driver for you, and then it assigns you your desired taxi or cab within just matter of seconds and minutes. Okay, so this is the entire algorithm and technique of how this geohash and quadrant tree or quad tree collectively work together to give you the fastest ride possible. So, however, in practice, hash values that are generated are not done using just like these numbers. They will use a combination of numbers and alphabet numeric characters, using which they will calculate the geohashes. Okay, so I hope you understood about the GeoHash and Quadtree and how do they work together. Now just let's look at the example which I told you earlier. Like we'll see a illustration of how do we convert a given latitude and longitude. Here we saw, right, we converted a latitude longitude into a geohash value using our geohashing algorithm. Let's see example of how this geohash algorithm works actually. Okay, so how geohashing is done? It is done in binary encoding. Now what does binary encoding mean? Binary encoding is kind of a binary search kind of thing. Okay, so just like you calculate, LCM and GCM for numbers, right? It's similar to that only, but using binary search. So what it will do, let's say we have a latitude value of 48.8566 and we want to encode it, okay, using 5-bit binary representation, because let's say our application requirement is till 5-bit, we'll subdivide it. Now what we do, let's say the latitude is 48.85, right? Now what we'll do, we'll normalize the latitude in range of -90 to 90 degree and normalize the longitude in range of -180 and 180 degree. Okay, now let's just see for the latitude. Okay, now we have a range of -90 degree to 90 degree with us. Okay, and then we calculate the midpoint. See, we are using the binary search, nothing else. So we calculated a midpoint is 0. Okay, now 48.856 is greater than 0. That means the number 48.85 lies in the upper half, right? I mean, 0 to -90 is the first half, 0 to +90 is the second half. So in the upper half, 48.856 lies. So because it lies in upper half, we'll have 1 in our, we'll add 1 to our binary representation of the geohash. Okay, now similarly the new range is 0 to 90 for us, right? Then again we'll divide, we'll again see that 48 is greater than 45, we'll add 1. So similarly we do all these processes. You see, new range became 48 to 90, then again we divided, the midpoint was 67.5, 48 is less than 67, so that's why it is in lower half. That's why we added 0 into our binary representation of the geohash. Similarly we go on dividing like this, and we generated 5 bits. Okay, if you see, the more deeper you go, I mean, let's say I want to divide it more, I mean, the more number of bits you want to have, the more precision we will have in the generated geohash. Okay, further you divide it, the more closer you'll get to the original, I mean the actual latitude and longitude of the user. Okay, but here for example you have taken 5 bits. Now you combine all these 5 bits, so it generated a binary number of 11000, combining all the bits from this binary encoding method, and where 1 represents the choice in the upper half region and 0 represents the choice in the lower half region, right? So latitude is this much, and let's say longitude is, using similar technique we calculated longitude. Let's say the longitude turns out to be 10001. Okay, now what we do, we'll interleave the latitude and longitude. That means we'll pick one character from longitude, one character from latitude, add it, then one from latitude, one from longitude, one from latitude, one from longitude. Like this you pick the bits one by one from longitude, then one from latitude, then one from latitude, 0 from longitude, 0 from latitude, 0 from longitude, so on and so forth. You generate the interleaved binary. Okay, we're basically interleaving those two things. Now once we get the interleaved binary form, what we can do, here we have taken base 10. Okay, you can use base 32 also. Base 32 means we'll have, let's say, 10 numbers. Okay, 0 to 9 are 10 numbers or 10 digits, and 22 alphabets. Okay, or base 36 you can use. So based on the application requirement, you can you can define your own base. Okay, for simplicity I have taken base 10 here, and converting this to base 10 it becomes 901. Okay, that means the user with this latitude and longitude, whatever, some longitude, let's say 2.5 degree, has the geohash value of 901. Okay, we can tell that the user is a part of this, let's say 901 block. Okay, just like we have 330, there will be a 901 block also. So that's how you calculate the geohash, provided you are given with the latitude and longitude value, okay, of that user. So that was about today's video. I mean, I hope you understood the two powerful concepts of geohashing and quadrant-tree or quadtree, and how they are, combinedly working together to generate the nearest available drivers for you in your ride app, right? So in today's video, we're going to discuss the system design behind designing a ticketing platform like BookMyShow or Paytm Insider, right? Which handles, during peak times when there is a very popular event or popular show like, let's say, Coldplay show or India-Pakistan Cricket World Cup match, right? The ticketing platforms experience a heavy load of concurrent user requests, right? And today we are going to discuss how during those peak times, this kind of ticketing platforms handles those loads and ensures smooth ticket booking. Although it has not been the case in BookMyShow since last few events where it has failed to, in some manner to allocate tickets for its users. So, but still we'll try to dive into the entire end-to-end system design. Okay. It will discuss all the underlying concepts that work together to make it possible for a ticketing platform like BookMyShow. Okay? So if you see, there are a lot of concepts, system design concepts that goes into play when you want to design something like this, like load balancing, rate limiting, database design, scalability, caching, locking, high availability. A lot of concepts are involved, right? They work together. So I'll discuss about all these things on a broader sense, but my main focus today will be discussing about rate limiting and event queues. Okay, like how rate limiting works in case of designing a ticketing platform like this, and how it enables a server without getting overwhelmed or overloaded to process request in an efficient and seamless manner. So as you can see, I have used this image from Geeks for Geeks, and here there is a leaky bucket. Now, what does a leaky bucket mean? It is a kind of rate limiting algorithm, right? Limiting, by definition, it means you want to control the rate at which request reaches a server, right? I mean the rate at which a server can process. You want to limit that, okay, based on the capacity of the server. If a server capacity is to handle, let's say, 10 or 20 requests per second, then even if there are 1,000 requests coming from the user, you want to have some kind of tool or some kind of algorithm playing here in the middle, which will control the inflow of request to the server. So that's what Leaky Bucket does. Leaky Bucket is one of the rate limiting algorithm. There are other algorithms also for rate limiting, like token bucketing, and a lot of algorithms are there. I don't remember the one of the other algorithm name. But today we're going to discuss about Leaky Bucket, and we'll see a practical code examples. How can we implement this actually? Okay, using Node.js and Redis and Kafka, etc. So stay tuned with me. So first, let's understand what does Leaky Bucket do. As you can see, we have a bucket here. Okay, we pour water in the bucket, and the bucket has a small hole below it, right? So you are continuously pouring water inside the bucket, but below the bucket, the water droplets drop one by one. Okay, in a controlled manner, right? So even if you are bursting the bucket with a flow of water, large flow of water, there is a fixed output or fixed number of droplets that comes in a fixed manner, right? What are these water droplets? These water droplets are the request. Okay, the user request that reaches the server. So now what happens if the bucket is full? Let's say output is slower, right, than the input. Then obviously the bucket will become full. As soon as the bucket is full, what happens? The excess water goes out of the bucket, right? So that means the excess water is discarded from the bucket. So this exact algorithm, okay, of leaky bucket is implemented to achieve something like rate limiting. So in rate limiting using leaky bucket algorithm, what we'll do, we'll have a queue. Okay, let's say we'll have a queue, okay, which will hold the request first. Okay, we can have multiple requests that is coming from multiple users, right? It will hold the request first, okay, and it will have a fixed capacity. That, as you can see, this bucket has a fixed capacity, right, to hold some water. So let's say this queue has a fixed capacity of 4. So, and we'll have servers, okay, which will have its own capacity at which it can process the request. All right. So at a given point of time, or let's say the server has capacity to process 2 requests at a time or 4 requests at a time. At a time, as in, let's say 4 requests per second or 2 requests per second. So if excess requests are coming, let's say suddenly the load on your app increased, right? So a lot of requests will be coming. Let's say 10 or 20 of requests are coming, but this queue has only capacity to hold 4 requests, right? And this server has capacity to process, let's say, 4 requests per second, right? So where the other 6 requests will go? So those 6 requests are nothing but this excess water, right? Which will overflow from the bucket or overflow from the queue. That means in simple terms, we are going to discard those requests and we'll send some message to the user like, too many requests or the server is busy or try after some time, and we'll notify the user, okay, about the same. So that's what the overall leaky bucket algorithm is about when implementing rate limiting using leaky bucket. So this queue is nothing but our bucket, okay, and these requests are the water droplets. Now I'm going to show you code examples how you can implement this leaky bucket algorithm using first, let's say, in a simple Node.js Express server. So we have Express rate limit package actually. So it will implement a rate limiter for your application, which is directly coupled with your Express.js application. Okay. So obviously in production you want to use this kind of tightly coupled rate limiters, but for your reference, let's just see these ones. Okay. So if you see, we have defined a rate limiter, how many requests it can manage per second. We have defined that also, max is equal to 100. And in case number of requests exceeds 100, right, at a given point of time, what we're going to send, we're going to send too many requests, please try again later. Okay. So this is a simple module given by Express rate limit package, which you can actually use to implement a directly coupled rate limiter. But in production, you will use something like a message queue like Kafka, or if you want, you can use Redis even. Okay, you can use Redis list to create a queue. Okay, which will queue the request, incoming request, and process them in a asynchronous manner, in an independent manner. So now let's just see a Redis implementation of our leaky bucket. Okay. For this case, I am using IO Redis package, and here what we have done, we have a function called add to queue, and we have a queue key called ticket queue. Okay. So this is basically a name of the list or name of the queue that we are creating. Okay. So that we can reference it later and get the request from this queue later. Okay. So what does this add to queue function does? It does nothing but it does a rpush. Okay. Redis.rpush. That means inside this ticket queue is a queue, basically it's a list. Let's say in the list side, in the right hand side, you are pushing the request ID. Okay, you are pushing the request in the list. Then we have a function called fetch from queue, which does nothing but it does a lpop, right? I mean, how does a queue work? You have a queue, requests are being pushed from the right one by one, and you want to pop from the left. So basically fast in, fast out manner. In a FIFO manner, you want to process, extract the request and process them, right? So this is what this fetch from queue function does. From Redis, we are using lpop, basically pop from the left hand side of the queue, this ticket queue, and then process the request ID. So here actually, once you get the request ID, you can store the request metadata like its payload, its different details about the user, the number of seats, all the information payload you can store in some other database. Using the request ID, you can fetch those payload and then process the request, initiating the payment, locking the seat, and all those further processing you can do. So for simplicity, I've just mentioned, we printed a console log here processing the request ID, right? So this is about the two functions that we can have in our Redis queue. Okay. Now, in order to process this, what we'll have, as I told, we have to process the request, right? Now, while processing, few things matter actually. Few things becomes important, like how many requests per second my server is able to handle. As I told, let's say we have a single server here, right? But in production, we'll have definitely a large number of server. I'm going to discuss about all these things. But for now, let's assume we have a single server here, which has a capacity of 4 requests per second. It can process 4 requests per second. So that's the maximum capacity it can do. Similarly, that's where we will be mentioning the processing rate here. Okay, let's say my server is able to handle 100 requests per second. That means 100 water droplets or 100 requests I will be extracting from the queue per second. And that's where we have mentioned the interval also. Interval is nothing but the milliseconds where we defined 1000 by processing rate. Okay, it's basically determines the frequency at which you want to fetch the 100 requests from the queue. And here we mentioned the set interval function, which actually, every 1000 by 100, that means every 10 seconds or every 10 millisecond, it will fetch from the queue, process it, and again keep on processing the queue. Every 10 milliseconds, if you process one request, in 1000 millisecond or 1000 seconds, we'll be able to process 100 requests. So that's how we're able to achieve the processing rate using this worker. Okay. Next, we have the main entry point of our application, right? Let's say as soon as our API called /purchase is hit, right? So this is where the user request will come, and first what we want to do, we want to add that request, right? Whatever request data is coming, we first want to fetch how many requests are there, whether my bucket is full or not, whether my key has capacity, whether my queue has capacity to hold new request or not, right? So that's why we first check the length, okay? Whether if queue size is exceeded, the queue max size. So queue max size, let's say 5,000 requests at max, right? So at max, we'll be holding 5,000 requests and processing 100 requests per second. And if any other new request come, which is beyond this max size, right? We'll just simply discard the request and send this error, right? Too many requests, try again later. Okay. If the queue has space in it, we'll then add the request ID. Okay. Here we have just simulated some random thing. I mean, request created a random ID, but here actually you can store the object ID of the request metadata, or you can store the entire request object itself. That's up to you how you want to design it. And then we are just adding the request ID to our queue using the add queue function, which is saw here. Okay. And then we are starting the server. So that's how you see we have implemented a rate limiter using Leaky Bucket algorithm using Redis. So here instead of Redis, you can use Kafka also. That is a better option to handle this kind of large scale application. So that was about the rate limiting and event queue. We learned about event queuing and rate limiting and how we can use this together to control the inflow of requests to our server. Now, why is this important? See, because everything has some capacity, right? A server is a machine also. It has some capacity. Just like if you add excess of water in the bucket, it just overflows. Similarly, our server has some limited capacity. That's why it's quite important to control the inflow of the request to the server so that it can run efficiently and smoothly without getting crashed or without getting overloaded. Okay. However, this is not the only concepts that are used while designing this ticketing platform like BookMyShow, because in practice or in reality, you won't be able to achieve this kind of ticketing booking platforms using a single server like this. As the load increases, we'll want to have something called scalability, right? So let me just give a quick overview of all the other concepts that are required to design this, because I'm not going to discuss everything in detail because I've created separate videos for all of these concepts. I'll just put them in the icon. You can go ahead and watch those one by one. But here I'll just give you a brief how each of these concepts can be utilized here to design a BookMyShow application, right? So first thing is scalability. During peak times, we can use horizontal scaling or auto scaling using cloud-based solutions, right? AWS auto scaling is there, right? In Azure also you can implement it in its own auto scaling, or you can use Kubernetes to add number of worker nodes or worker servers, right, to handle excess load, right, the incoming load based on real-time demand. So we can implement a microservices based architecture. So that means we can split the different functionalities like payment, then ticket booking, ticket locking, then seat booking, all those things. We can divide it into multiple microservices, and we can process an incoming request and communicate with these microservices in an asynchronous or synchronous manner to get the entire transaction done. Second concept is load balancing. Okay. So what we can do, we can use some global load balancers like Amazon Route 53 or Cloudflare to distribute traffic across multiple geographic locations. So that's the job of the global load balancer. Next, we can use application level load balancers like HAProxy or Nginx or Elastic Load Balancer in AWS, right? Which will do what? It will just distribute the incoming traffic, right, or incoming request among multiple instances of our server. Okay. We'll have multiple instances of our server. So you can use the application level load balancer to route the request to these worker instances in a even manner, right? So that's how the two global load balancer and application load balancers work. Then we can leverage caching also, right? In caching, what we can do, we can cache frequently accessed data, right? Like the seat information or seat availability, the pricing information, the seat layout. These are frequently accessed information, right? When there is a event going on and people are willing to book for that show or event, we can actually cache this frequently accessed information in some cached server, right? Like Redis, okay? And obviously you want to have a right through caching mechanism in place so that you can update the cache data in real time, because you want to show which ticket is booked in real time, right? If someone else has booked just now, you want to immediately reflect it in the seat layout to other users. So you want to have a right through caching mechanism. So if you want to understand more about this caching, right through caching, all those things, click on the icon. We will there I have discussed about this in details in a separate video. Okay. Then we can work in terms of database design, right? We can have database sharding, database partitioning we can do. Then we can have multiple read replicas of our main database, right? So when the load increases, let's say millions of people are trying to book ticket for India versus Pakistan World Cup match. So we'll have enough read replicas of a database server so that they can, extract information. Okay, caching is another thing, right? Caching is just extra layer which you are adding, but main thing is database. If you have enough read replica, data will be read from those read replicas. Okay, and then we can have some locking mechanism, right? You can use some pessimistic locking mechanism to lock a given ticket. Okay, for a temporary amount of time. So when a user selects a particular ticket, you can actually lock that using some pessimistic locking mechanism, and that seat will be booked for a temporary amount of time. If the payment is not done, we will actually utilize a timeout functions to release the lock from that seat so that it will be available for others also. Okay, you can ensure high availability by having redundant servers, redundant read replicas. Okay, and you having a distributed message queue, high throughput message queue like Kafka, and you can use replication to ensure high availability, right, as we discussed. So all these things are quite important, and you can actually, in order to ensure high availability, you can do implement retry policies, right? Let's say if someone is trying to book a particular ticket, in the background you can retry it, let's say for 2-3 times if the request fail. Okay, so you need to ensure that you have retry policies in your application logic. That's how all these concepts, right, work together to help you design a scalable, highly efficient ticket booking platform like BookMyShow, Paytm Insider, or Zomato District. Okay, so our main focus was to show you today how rate limiter actually plays a crucial role in designing this kind of ticketing platforms along with event queues. We saw code examples in Redis and using the Express rate limiter package. So I hope you understood about the rate limiter and event queues in details in this video. If you have any doubts about whatever we discussed, put them in the comment section. I will be sure to answer them. So today we are going to discuss something about really cool. How big platforms like Instagram, Twitter check if a user exists in their database or system or not. Let's say you are asked to solve this problem. How do you approach it? So it seems simple, right? I mean, you just type in the username and hit search button and it just works and tells you whether the user exists in the database or not. But behind the scenes, things are a bit more complex. How do these big platforms handle this kind of scenario when there are billions of users in their database, right? So let's dive into that and discuss how do they solve this. So think about it. You have billions of user records, right, in the database, and you need to check if a user is there or not. So the first and straightforward approach would be to use a direct query. Okay, this is the most basic way you can do this check, and it would be to run a direct query with the database, and just the database will return if the user exists in the database or not. Okay, it sounds simple, right? But hold on, not so fast. If you are having billions of records, searching through the entire database can be very time consuming. It will go very slow, really slow. Okay, and if millions of people are searching at the concurrent time, at the same time, if millions of people are searching for the usernames and you put a lot of pressure on the database, then it will obviously break down. The system will break down, and the performance will be drastically reduced. Okay, so that's when you get very slow response times, or system can crash under too much load. Okay, so these are the problems that we face in the very pretty straightforward approach. It won't work for a larger database, and slow response when millions of parallel requests are being done. Okay, so this is where things get a bit smarter. Okay, so instead of going to the database every time, what we'll do, we'll use the mechanism of caching. Let's go to the next one. So, what do you mean by caching? So, cache is like a shortcut, right? It stores the result of the most recent queries that is run in the memory. And if someone asks the same question, ki, hey, does user XYZ exist in the system? So the cache already knows the answer and it can deliver it super fast. Okay. So no need to go back to the database. For example, if I want to check if Pritham Kesari exists in the database or not, first the server will go to the cache memory. It will check whether if the user Pritham.Kesari exists in the cache memory or not. If it doesn't find, then it will go to the database, it will query the result and update that record in the cache memory, so that next time if someone else comes and queries for the same username, the server will able to fetch it from the cache. But here's the thing, I mean, what if the cache doesn't have the info, as we discussed, right? We call it as cache miss, right? Or what if the data in the cache is outdated? For example, the server updated the Pritham.Kesari username in the cache memory, but the user was deleted. But the username still exists in the cache. So it can wrongly tell the other users that Pritham.Kesari username exists. This is where cache, outdated cache or stale data in the cache creates a problem. Okay, and obviously there are other problems also about high memory usage in cache. Then if a cache miss occurs, then we have to again query the database, right? So back to the square one. Now the problems will be as same as the direct query approach which we saw in the above slide. Now the question is, how do we handle this situation then? So this is where something clever comes into the picture. Okay, it is known as Bloom filters. All right. So in Bloom filters, so Bloom filters are, they're just like magic, and the concept is actually very simple. Okay. So Bloom filters let us quickly check if a user might exist without needing to go to the database. I am emphasizing on the word might. Okay, why? We'll understand this in a while. Okay, so the cool part is a Bloom filter will never miss a user who is in the system. Okay, but there is one catch in Bloom filter. Sometime if the user doesn't exist in the system or it is not present in the database, it can falsely tell that that user is present in the database. Okay, which is a case of false positive. Okay, it's a scenario of false positive output. But that's okay because we can handle that, and how to handle that false positive case, we'll discuss that in a while. Okay, so now this Bloom filters might be sounding confusing to you, so we'll discuss that with an example. Okay, so here's how the Bloom filters work. For example, when we add a user to the system, for example, a user is coming and he's typing in this username while creating his account. Okay, Pritham.Kesari. Now what the server will do, the server will send this username to the Bloom filter. Now the Bloom filter will hash the username using several hash functions. In our case, we have used 3 hash functions, namely h1, h2 and h3. Here k is equal to 3, which is nothing but the number of hash functions that we want to use currently. And we have a bit array of size 9 here. Let's say the size is m, and in our case m is equal to 9. So we have a bit array of size n. How do we determine the value of k and m? That's a separate topic. We'll discuss that about in other video. So these hash functions, what do they do? They will consume this username, okay? And this username will be the input to each of the hash functions, and they will spit out some indices, okay? Let's say when we inputted this Pritham.Kesari username, it spitted out 3 hash values, okay? For example, 0, 1 and 7. So what we will do, we'll use these indices, okay? We'll go to the bit array and check the value of these index positions, okay? For example, at index 0, we have 0, index 1, we have 0, and index 7, 0, 1, 2, 3, 4, 5, 6, 7, 7. So all of them are 0. For example, if any of the indices is 0, for example, at index 0 only we have the value of the bit array as 0, that means the user does not exist in the system, okay? Let's say there were no users initially in the database, okay? So these hash functions create a bunch of indices in a bit array, and we set those bits to 1. Now because the index value is 0, so what we will do, we'll first insert this user in the database, okay? Stating that, yeah, now this user is there in our system. Let me just reduce the size a bit, okay? Then for this username, we got 017 as the index output rate. So we'll change this indices to 1. 0, 1, 2, 3, 4, 5, 6, 7. So when another user will come, okay, and he will again query for the same username. He asks, does this username exist? Does this username called Pritham.Kesari exist? So what we will do, we will run the username through the same hash functions. It will again spit the same index value, and we'll check if all the value of the bits array at this index positions are 1 or not. In our case, yeah, all those are set to 1. So we'll return an output that yeah, that user exists in the system. All right. So if all the bits match, obviously, then the filter says yeah, the user probably exists in the system. Okay. So even if one of the bit is not set as we discussed, the system will confidently say that the user does not exist in the system. So for example, let's say another user ID comes called p.casery, for which the user ID that we are querying is p.casery, and the index it gave in the output are 2, 3, and 5. Okay. So again, we'll go to the bit array to check at this index position, and we find that at the index position 2, which is this position, the bit is set to 0. That means we'll confidently say that this user does not exist in the system. We'll again send the output as no to the user, and then we can safely insert this user ID in the database. Right? So as we discussed, in case of Bloom filter, if the system checks a username and finds all the bits, not that all the bits are set to 1, it says that this user might be in the system. It's not 100% guaranteed or 100% sure, right? How and why, we'll see that in the next example, which is a false positive case. But if any one of the bit is set to 0, then the system is very confident. It can definitely and confidently say that the user is not in the system itself. Okay, and that's the trade-off actually. Okay, for example, if I let's say discuss about this username, let's say right now we are discussing about treat.casery username. Okay, another user comes and he tries to register with this user ID, and for example, for this treat.casery we got this index as the obviously I forgot one step. After inserting p.casery in the database, you have to set these bits as 1. So 0, 1, 2 will be set to 1, then 3 will be set to 1, and 5 will be set to 1. So p.casery is also now in the database. Now let's say another user came to register into the application with this user ID called treat.casery, and the indices that that the hash functions generated are 0, 3, and 5. Okay. Now if we see, index 0 value is 1, index 3 value is 1, and index 5 value is also 1. And this Bloom filter will give an output that yes, this user exists in the database. But if you look at the database, we don't have treat.casery in our database, right? This user is not present in the database. So this is a case of false positive. Okay. As we add more number of users, right, the chance of getting false positive goes up basically drastically. To minimize the occurrences of such false positives, right, what we can do, we can find an optimal value of k and m. So as we discussed, we'll create a separate video for this, how to find the optimal value of k and m in Bloom filters. So that's the catch actually. The amazing part is Bloom filters use very little memory, right, because they store only bits, right? It's a bit array basically. So they use very little memory and work really fast. Okay, and which is very perfect for handling millions of parallel requests. Now the question in your mind will be ki how do we handle this case of false positives, or how do the big applications handle this case of false positives? Okay, so if the Bloom filter says yes, the user exists in the system, and it's actually wrong. In our case, treat.casery was not present in the database, but it still said that the user is present in the database. So what we can do, the system can double check with the database. Okay, so every time there is a yes output by the Bloom filter, what we will do, we can double check that with the database, and every time there is a no output. Okay, every time there is a no output with by the Bloom filter, we can confidently say that the user is not present. So in case of yes, the output is a probabilistic output, and in case of no, the output is a deterministic. It is a confident output. Okay, 100% confident output. In many systems, they use a mix of cache and Bloom filter also. For example, after getting a yes from the Bloom filter, instead of directly querying with the database, what we can use, we can fall back to the same approach. We'll introduce a layer of Bloom filter here. Let's say the Bloom filter box is here, right? The server will first interact with the Bloom filter. Okay, If the output is no, then as we discussed, obviously, no need to cross check further. If the output is yes, it can cross check with the cache memory first. If it is still not present in the cache, it can go to the database and query the database. So a caching layer similar to this similar caching layer we can incorporate here also. Okay, just to make the things run quite faster. So this layered approach of Bloom filter, caching, and direct database query. Okay, we layered these three approaches together, and this layered approach lets the platform handle huge amounts of read queries, right? About whether a record exists or not, or whether a user exists or not in the database or system. It enables to handle such huge amounts of traffic while staying fast and efficient as well. Okay, so that's where the concept of Bloom filters becomes very interesting and very useful in large scale system designs. All right, so just to wrap it up, when platforms are checking if a user exists among billions of records, they start with a Bloom filter check for a quick answer. Okay, then they will move to caching. We'll introduce a caching layer as we discussed, and they will only hit the database when they are absolutely required to. Okay, so this balance keeps the things running smoothly. All right, even when dealing with millions of users at once. If you have any doubts about Bloom filters or the entire video that we discussed just now, drop your comments, drop your question in the comment section. So I'll be sure to answer the questions. So today we are diving deep into the math behind Bloom filters, okay? So specifically we'll explore how to calculate the false positive rate and how to calculate the optimal value of k and m, where k is the number of hash functions and m is the size of the bit array that is used by the Bloom filter, okay? Actually, this video is an extension video to one of my previous videos about Bloom filter, where I discussed how Bloom filters work and why is it required. And I strongly recommend you that you watch that video before watching this. So click on the I button above to watch that video now. So first watch that video, then come back to this video so that you will get the clear picture about Bloom filter. So let's get started. So first, a quick recap of how Bloom filters work actually. So a Bloom filter is a bit array of size m that starts with all bits set to 0. Okay. So when you want to add an element, or let's say you want to add an user or check in user, k hash functions map that element to k positions, okay, in the bit array, and these positions are set to 1. So here k is the number of hash function and m is the size of the bit array. So now when you want to check whether an element or an user exists in the database or not, the same hash functions will map the element to k positions like this. And if all those bits are set to 1 in those positions, the Bloom filter says that the element might be in the set. But if any bit is set to 0, the element is definitely not in the set. So that's how Bloom filter works on a higher level. Okay. But here is the catch. Because Bloom filters allow multiple elements to map to the same bits, false positives can happen, right? So a false positive is when the filter incorrectly says that the element is in the set, even if it is not added in the set or database ever, right? So that's the case of the false positive. So how do we calculate the probability of this false positive? Like how probable is the false positive occurrence, okay, in a Bloom filter? So let's dive into the math now, okay? So let's break it down step by step. Imagine we have n elements or n users like this, which we want to add into the database, and each element gets hashed to k positions using this k hash functions into a bit array of size m, okay? So now let's play some math, okay? So now what is the probability that a specific bit remains 0, okay, after you insert one element? So the formula is 1 minus 1 by m. Remember, m is the number of bits in the bit array and k is the number of hash functions. Now this formula 1 minus 1 by m, it's pretty intuitive, right? I mean, there's a 1 by m probability or 1 by m chance that a hash function picks a specific bit out of this bit array and sets it to 1. So the probability that it does not get picked by one hash function is 1 minus of that, right? That's why 1 minus 1 by m. So probability that a specific bit remains 0 after inserting one element with one hash function is 1 minus 1 by m. Now since we are using k hash functions for each element, the probability that the bit is still 0 after all k hash functions have been applied. So it becomes 1 minus 1 by m to the power k, because each hash function tries to set a different bit. So this raises the probability to the power k. So this probability raised to the power k becomes this, right? So that's the step number 2. Now, what happens when we insert more elements? See, till now we are discussing about inserting only one element or one user. Now let's think of a case when we want to insert n elements. So after adding n elements, the probability that a particular bit remains 0. Okay, that means it is not set. Even after k into n hash operations, that is 1 minus 1 by m to the power k into n. Okay, so again, this probability is raised to the power n because here we are talking about n users or n elements. Okay, now let's flip this idea. Alright, now what's the probability that the bit is set to 1 even after inserting n elements with k hash functions? So the probability that a specific bit is set to 1 after inserting n elements with k hash functions is 1 minus this probability, right? 1 minus this probability. So 1 minus this probability becomes this formula. If you see 1 minus 1 by m to the power k into n. So now we know the probability that any particular bit is set to 1 after inserting n elements is equal to this. Now comes the crucial part, okay? That is calculating the false positive probability. Now let's say you query an element or user that was never inserted into the database. For a false positive to occur, as we have discussed previously, all k of the hash functions for this new element have to point to bits that are already set to 1. Okay, that means all the indices that are splitted by the k hash functions, right? If all those indices are set to 1 already in the bit array, then we say that the user is already existing in the database. So we need to find the probability that k bits are set to 1 after inserting n elements with k hash functions. Okay, again, in order to calculate the false positive probability, we need to calculate the probability that k bits are set to 1 after inserting n elements. So this is the above probability raised to the power k. So we get the formula for false positive probability as 1 minus 1 by m in bracket raised to the power k into n, the whole raised to the power k. So this probability raised to k basically. Okay, so this expression gives the probability of a false positive in a Bloom filter. It might look complex, but all we are really saying is, for a false positive, each of the k bits we check must already be 1. So that's what it all boils down to, right? Now for a large n, we can make this equation easier to work with. So when m is large, that means here the number of the bit array is large. We use a mathematical approximation to simplify this. We use Taylor series approximation like this. So this approximation tells us that ln of 1 minus x is approximately equal to minus x for smaller x. Okay. Now in our case, x is equal to 1 by m. Okay. So for large m, x is small, right? I mean, if m is larger, then x will become smaller. So hence in our case, if we replace x with 1 by m, we get ln of 1 minus 1 by m is approximately equal to minus 1 by m. Now exponentiating both sides, we get 1 minus 1 by m is approximately equal to e to the power minus 1 by m. So 1 minus 1 by m is approximately equal to e to the power minus 1 by m. So using this approximation, we can rewrite this false positive probability as this formula, right? False positive probability is approximately equal to 1 minus e to the power minus kn by m, the entire thing raised to the power k. So basically we replace 1 minus 1 by m with e to the power minus 1 by m in this formula. So this is the simplified version of the false positive probability. So the key takeaway, the probability of a false positive depends on 3 factors, right? As you can see here, the size of the bit array m, the number of hash functions to use k, and the number of elements that you are willing to add to the filter, right? Yeah, alright. Now that we understand how Bloom filters work and how to calculate the probability of false positive, let's take a step further, okay? And how do you choose the optimal value of k, that is the number of hash function, and the m, the size of the bit array. So this is crucial because it directly impacts the space efficiency and the performance of our Bloom filter. Okay. Now you already know that the false positive probability is given by this expression. Okay. For larger m. So here n is the number of elements that we want to store, k is the number of hash function, and m is the size of the bit array. Now our goal is to minimize this false positive rate while keeping the bit array as small as possible to save memory. Now let's change the slide. So now let's first tackle the number of hash functions to use, that is k. So it turns out that there is an optimal number of hash functions that minimizes the false positive probability for a given m and n. Given that m and n are fixed, we can calculate the optimal value of k. How do you calculate that? Now the optimal k can be derived by taking the derivative of the false positive probability formula. That is, we can take the derivative of this expression with respect to k, assuming m and n are kept constant, and we equate it to 0. Because we are trying to find the minima of this function, right? But don't worry, I won't take you through all the calculus steps here. So instead, I'll just give you the result directly. So the optimal number of hash function is approximately equal to m by n into ln of 2. Okay. Again, to repeat, how do we find this value? By taking the derivative of this expression with respect to k, keeping m and n constant. The optimal k depends on the size of the bit array m and the number of elements n. Okay, as you can see here. So this means that the more elements you want to store, or the larger your bit array, the more hash functions you should use. Okay, but that is up to a certain point. Beyond that point, using too many hash functions actually increases the false positive rate. Okay, now let's move on to the bit array size m. How big should be the bit array to keep the false positive probability under control? So you can actually derive a formula for m based on the expected number of elements n and the desired false positive probability rate p false. Okay. Now the optimal size of the bit array is given by m is equal to minus n into ln of false positive probability rate that we are expecting, then ln 2 ka whole square, right? Again, we are skipping the calculus steps for simplicity. So let's break this down. N is the number of elements you plan to insert, and p false is your target or desired false positive probability. Say something like 1% or 0.1%. Basically, it's the error rate that you can afford, okay, or the error or the fault or the false positive probability that you can afford in your Bloom filter implementation. So the logarithms came from the math involved in minimizing the false positive rate, just like we did for k optimal. So this came from that. So now you have two key formulas. The optimal number of hash functions k, which is equal to m by n ln of 2, and optimal size of the bit array m is given by this expression. Now let's put this into practice. Okay, suppose you want to store 1000 elements or 1000 users in a Bloom filter, and you can afford a false positive probability or the error rate of 1%. Okay, so using this formula, we calculate the value of m, and we get that m is equal to 9586 bits approximately, right? So that means you'll need about 9586 bits in your bit array to keep the false positive rate around 1% and to store 1000 users. And for the optimal value of k, using this m value and this formula, we can calculate the optimal value of k as this expression, which evaluates to approximately and roughly equal to 7. Okay, so in this case you would use around 7 hash functions. Okay, now let's take a moment to visualize all of this and the trade-offs that is involved. Increasing the value of m, that is the size of the bit array, decreases the false positive rate, but you are using more memory. Okay, similarly, increasing k to the optimal number reduces the false positives. Okay, but going beyond the optimal point can actually make the Bloom filter less efficient. Okay, so the key here is to balance these two things. By carefully choosing a balanced value of m and k, you can design a Bloom filter that efficiently balances memory usage and the false positive rates. Okay, so to summarize, the optimal number of hash functions k is around m by n into ln of 2, and the optimal bit array size m depends on the number of elements that we want to store and false positive rate p false. So by tuning these parameters, you can get the most out of a Bloom filter for your specific needs and use case, right? So in today's video, we're going to discuss one of the important algorithms that plays a crucial role in implementing a feature like autocorrection, right? You must have seen this autocorrection feature when you type some wrong word. In Grammarly, it autocorrects it with the correct word. Or let's say in WhatsApp, when you type something, it gives you suggestions, right? It is giving three suggestions to you, right? The heart of this autocorrection technique is the trie data structure, okay? TRIE, trie. So what does trie data structure means? So trie is it's kind of a tree of characters. Okay, I mean, so basically how trie works is it's a we store a predefined dictionary of valid words in the trie. Okay, as you can see we have a root node. Don't worry, I'll show you the code also for this, how to implement a trie in C++. As you can see how we are storing the words is each word is broken down into characters basically and added as a sequence of nodes here, right? As you can see CAR, then and two words if they share a common prefix they will have the same path along the tree, right? CART we are having and then CAT we are having like this. So for this example we have taken only two nodes C and D and there will be other nodes also like this. Okay, now let's just see the code once. Okay, how to implement the trie. So if you can see here, so this is the structure of a trie node. This code I have taken from Geeks4X just for reference. Okay, and each node, if you can see, there is a array of 26 pointers. Each node has an array of pointers called child nodes. Okay, and each node has a property called word end. Okay, why 26? Because A to Z are 26 characters. That's what we are considering here. Okay, now how do you insert a word into a particular trie? And for that we'll have this insert key function. If you can see here, what do we do here? Basically we traverse character by character. Okay, we start from the root and traverse character by character, and here we are using the ASCII character computation to get the ASCII value of this character, and we'll use that as the index for this list. Okay, for this pointer list. If the particular character is not present in the tree, we create a new node and we move on to the next node. Okay, so basically we'll insert C, then insert A, then insert R. So that's how we insert the particular words in the trie. Now in order to search a given key in a trie, this is what we do. We basically traverse the trie, okay, across the length of the string, and we traverse the trie character by character until we reach the word end. Okay, so that's how we try to search a key in a given trie. So this is the code to implement a trie. Okay, now we'll see how autocorrection actually works. Okay, so what does the autocorrection technique do? It's try to find the similar words, right, which is matching with the corresponding input word. If you have inputted, let's say, a wrong word like this, CAAR, it will try to find out a similar matching words or list of matching words. And how do you do that? It uses two techniques basically. Okay, the first one is the edit distance. It calculates the edit distance. Now what does mean by edit distance? So edit distance basically measures how many edits or small changes. That means the small changes can be a insert operation, okay, deletion operation, or substitution operation. Okay, basically we want to insert one character into that given input string, or we want to delete one character from the given input string, or we want to substitute a given character from the input word string. So edit distance basically measures how many operations we need to do. Okay, any one of these operations or any one or more of these operations, how many of these operations we need to do to convert this user input word to a valid word in the trie. Okay, so basically to calculate the edit distance, there is a popular algorithm called Levenstein algorithm. Okay, the algorithm name is Levenstein algorithm. So it basically, allows for efficient calculation of the minimum number of edits, okay, that is required to transform a given string into a valid string in the trie. So we are not going to discuss in about this Levenstein algorithm, but in brief I'll tell you the two main important input to this algorithm are the input word, obviously, with the user is given, and a parameter called max distance. Okay, so now what does max distance means? This exactly means the number of operations, okay, of this that is allowed. Okay, so let's say we assume that max distance is 1. So you can choose your own max distance based on your application requirement, like how many edit operations you can allow. Let's say we assume max distance is 1. That means we are allowing only one operation, only one of these operations using this Levenstein algorithm and this max distance calculation. Let's say the input word is CAAR right here. Now if we employ edit distance technique in order to convert this CAAR, right, you can convert it to a valid word called cat. If we just substitute this A for T, right, basically it becomes CATR. Even it is not a valid word, but the substring of this CAT which falls along the way, it is a valid word. Okay, and how do we determine it's a valid word? Because as soon as a word is valid, what we do, we mark that node. Okay, end node, right? Not end node, or the word end is true. Basically, if you can see, we had this word end flag, right, for a given node. So if a particular node makes a valid word, right, then we mark it as red. So this also has to be marked as red, because dog is a valid word, then doge is again a valid word. Okay, so word end doesn't mean the node ends there or it's a leaf node. It's not like that. It just marks that the path that we have traversed so far, okay, it's a valid word. Okay, that's what it just does. Now similarly, if we just remove this a from this car, we get cr, right, which is again a valid word. So using just max distance as 1 in this case, that means here we just performed one substitution operation to get CATR from this, and here we performed one removal operation to get car from CAAR. So using the max distance of 1, we are able to get two candidate, okay, two candidate solution for our use case. So we have got now cat and car, right? And the next technique to generate candidates for similar words are the prefix matching, right? If you can see, when we'll be searching for this word in the trie, okay, using our search algorithm that we have written here. So what we'll do, we'll first go for C, right? C is there, obviously. The next character is A. A is present in trie, so let's move to the this node, A node. Then the next character is again A. Then we see that there is no node. I mean the node pointer for the character A is empty here, right? That means we have reached until this node, and after that the pointers are not available. So in this case, what we'll do, we'll utilize the prefix that we have traversed so far, right? So till now we have traversed C here, right? Now we'll utilize this and then generate words that are coming after it. Okay, from this prefix we'll traverse all the valid possible paths in the trie and put it in the candidate list. So the words we get are CART, and let's say there is one word called CARE also. Okay, and this will also be marked as red because this is a valid word, CRE. So these are the, let's say, some of the candidate solutions we got. Okay, let me just color it in a different color. Now using this candidate solution, then the third technique we want to employ is we want to employ a ranking algorithm on this, right? So what we can do along with this each node, right? So in each node we can introduce a parameter called frequency. Along with word node we can have another property called frequency in each node, which will store how many frequently the particular word has been used by the user. Okay, let's say the word cat is used 10 times by the user. So this node will have frequency as 10. Let's say the word cart has been used by 30 times. So this node will have frequency as 30, right? Now once we got these candidate solutions, right, then what we'll do, we'll use those frequency value to rank this, right? Let's say cat had frequency as 30, then car had, let's say, 45, cart has, let's say, 33, and care had, let's say, 2. So then what we'll do, we'll rank them according to their frequency to give the top 3 suggestions, let's say. In our case it will be car, cart and cat, let's say, right? So these are top 3 suggestions that we can give to the user. I mean, this is just one naive explanation of how we can use the trie algorithm to implement something like this autocorrection and spell checkers. That's how, we use trie algorithm along with edit distance, then prefix matching and this ranking. So these 3 techniques along with the trie algorithm to build something like a autocorrection algorithm for us, okay, or autocorrection tool for us. So I hope you understood about the trie data structure in detail. If you got any doubts about whatever we discussed in this video, put them in the comment section. I'll be sure to answer them. So in this video, we are going to discuss the system design behind Instagram Reels. So, and we'll discuss how Instagram, serves you Reels so fast, right? You just keep on scrolling and it just, seamlessly displays Reels for you without any lag, without any slowness as such, right? So let's just discuss how does it do that. So before that, I'll suggest you to go through this video where I've discussed about CDNs, okay? Because CDNs is a crucial part of distributing content so fast. So we first watch this video. So in CDNs, we have a central server here, okay, and we have edge servers like this, okay. In different physical locations, we have edge server. This edge server may not be the single server. Again, there will be multiple distributed servers here. It's not a single server. Here also there will be multiple distributed servers. In brief, what does this edge server do? Those edge servers basically cache the data, right? If let's say someone uploads an Instagram video here in the central server, that video is cached in these edge servers so that they can be served to the user in a quite seamless and fast manner, okay. So in today's video, we are going to discuss how inside this edge server a very important system design algorithm called consistent hashing is used to serve you content in a complete seamless manner without any breakdown, without any lag, or without any hiccups, okay. So before discussing about consistent hashing, first we'll discuss about the normal hashing first, okay. I mean, how does normal hashing works in terms of a distributed system? Let's say we have this we have some videos like this, okay. So these are the reels, okay. Let's assume like this. These are the reels object in the database, okay, which the users have uploaded, okay. Let me just color it with some different colors so that it will be useful to identify later in the explanation, okay. Let me just do it quickly. So these are our videos, all right. Now how does a normal hashing works is we will have a hashing function here, okay. This is a hashing function that we will have. What does this hash function will do? It will take the object IDs, okay. Each of these objects, video objects, will have its object ID, right? Some kind of identifier, like we have incremental ID in SQL, some Mongo ID in Mongo objects, right? So this will have its own ID. So using that object key or object ID, what we will do, we'll pass this to a hash functions, right? Each of this object key will be passed to the hash function. It will spit out a hash values for us within a hash space. Now what does a hash space means? Hash space is nothing but a list of range or range of numbers like this. Let's do, we have a range of numbers like this. So this is, let's say, x0, this is, let's say, x1, and similarly we have xn. So this is our hash space. And once the object keys are passed into this hash function, it generates a hash value from this hash space, okay. Now once the hash values are generated, what we will do, we will divide it with a value called n. So this hash value that it has generated, we will divide it, or we'll get the modulo n, where n is nothing but the number of servers that we have, or number of distributed, let's say, cache servers, right? Or database server, cache server, it can be anything, any distributed server. So in our context, it's a, let's say, distributed cache servers. So let's say we have 3 servers like this with us. Now once the hash values are generated, we are dividing it, let's say, number of edge server, in our case it's 3, so we'll get the modulo 3 of that hash value. So it will generate a number between 0, 1 and 2, which will determine which server the values or the object will be cached in, right? So let's say after the hashing was done, we identified that these videos will reside like this, okay, in an even manner. Now this is fine. There is no issue with this entire normal hashing technique until and unless we have the number of servers as fixed, until and unless we are sure that none of our servers will fail ever. But that is not the case in a real life scenario, right? So systems can fail, the servers can fail, or the network connectivity between the user and the servers can fail, right? Or the server may become unresponsive. So during those time, what will happen if one of the server fails, or let's say we add one more node into the distributed architecture to handle more load. So in both the cases, the issue with this normal hashing is very, I mean, it's vast, okay? Because let's assume the server was dead, okay? This was dead. The server, so somehow the connectivity between the user and the server become unavailable. Now what we will have to do, now the number of available servers changed, right? It became 2. That means for all the objects, all these objects, the hash value has to be recalculated, and all these videos will be redistributed among these 2 servers, okay. So what does it do? It will involve a lot of to and fro and lot of rebalancing and the movement of data movement across servers, which is not only time consuming, and in that period your application will become very unresponsive. It will not work properly. Again, these 2 servers will itself become unavailable, or become unresponsive very fast, because they are involved in exchanging, managing the data transferring, right? So this approach becomes very costly for us. Okay, with this. Even if let's say we are adding one more server to our distributed architecture, in that case also the n value changed from 3 to it has become 4. Again, you have to calculate hash value. Basically, you have to rehash your entire object storage, or you have to calculate the hash value for each of your objects again and distribute the loads evenly across all the nodes. Okay, so in order to handle this issue, we have a very important system design algorithm called consistent hashing. Now in consistent hashing, what do? We have this hash space. Okay, hash space is nothing but a range of numbers that this hash function can generate, and a good hash function will generate hash values which will be uniformly distributed across this space. Okay, now in consistent hashing, we'll get rid of this thing first. We won't perform this modulo operation anymore. Okay, this modulo operation that we are doing here, or we won't do that, will directly act on the hash value that has been generated. So what we'll do now, we will take this hash space, okay, then join this together. Okay, basically we'll join this two and together to form a ring or circle. Just think it like you have folded an entire hash space like this and formed a ring. Okay, so in this case what will happen, we have a hash ring now. Okay, or consistent hash ring we have. Let me just so we are representing this hash space in terms of a circular hash ring. Cool. Now what does this hash ring do? In this hash ring, we'll not only calculate the hash value of these objects, along with that we'll calculate the hash values of these servers also. Each of these servers has their own IP address. So we'll calculate the hash value of each of these server and along with the object keys and place them on the ring. For example, let's say we calculated the hash values of our server A and it turned out to be, let's say, x3 or x5 or some number. Okay, let's say 2005. So what will happen, we will place it. Now what we'll do, we calculated the hash value of this server or server's IP using the same hash function. We calculated hash value and we place it here, let's say. Okay, similarly we calculate all the hash value, okay, for all our other 4 servers that are available, and we place them on the ring like this. Similarly, using the same hash function, what we'll do, we'll calculate the hash value for these objects also. Like this, we calculate the hash value for all of these objects and we'll place them in the hash ring. How do we place these objects in the hash ring? First of all, we have to think that as soon as a user comes and uploads an Instagram video or Instagram reel, what we'll do, we'll first upload that in the main storage, just like we saw here, right? We'll upload it in the main storage, and then when we'll be distributing it across the edge server or caching it across the edge server, what we'll do, we'll first calculate its hash value. Then in the hash space, or in the hash ring, we'll see which object is the nearest available server. Okay, because we have already hashed our servers, right? We have already hashed our servers and placed them in the hash ring. So we'll move in a clockwise direction in this ring, and then we'll find out which server is the nearest location available for this server. Then what we'll do, we'll then just physically place that video or cache that video on that server. So that's how actually that caching is done, because you won't have servers in a circular manner, obviously, right? In physical location, they will be placed across different regions, but conceptually, first you will calculate the nearest available server for this object, and finally physically you will just place that on that physical server, right? Now when a user comes and watches reels, and let's say he just scrolls on this reels, and he just, let's say, request for this green reel, right, or green video, what our application will do, it will then pass its object key to the hash function. It will find out the nearest available server, okay, in that hash ring, then query the IP address. It will send a request, and using the IP address of this server, because we will be storing metadata also along with each of these nodes in this hash space, we'll query that particular server using its IP address and access the content from that server. So that's how this hash ring works. Now, how does it deal with the two problems that we saw in a normal hashing? Let's say one of the node becomes unavailable, it fails. Let's say it failed, okay? For some reason it failed. It is not a part of the ring anymore. Now what we have to do, we just simply have to move these two objects only, because earlier this blue and green objects were a part of this server, right? Now this became unavailable. Now what you have to do, you have to only move these two things or two objects to this, right? So we'll only move these two objects to that server. Okay. As you can see, unlike the normal casing where we had to recalculate the hash values again, then we had to again transfer the entire set of objects or all the objects across multiple servers. We don't need to do that here in the consistent hash. Similarly, if we have, let's say, instead of removing, we are adding, let's say, one more server, okay, in this, somewhere around this. If I just add one more server somewhere around this, let's say the load increased and I added a new server and I calculated its IP address and I got it IP address and calculated the hash value using the hash function. I place it here in the ring. So in this case, what I have to do, I only have to move this object because this object earlier was a part of this server, right, or this cache server. Now I have to move it to this server. So the data transfer, the amount of data transfer across servers been reduced by a lot, right? So that's what the benefit of consistent hashing is, using this hash ring concept. But consistent hashing also comes with one problem, okay? The problem is, what if when we are generating the hash values for our servers and placing it in the ring, what if they are, largely skewed? Skewed as in, let's say, all of our, let's say, edge servers are like this, okay? That means, and let's say we have lot of videos which are falling in this portion. So here if you can see, this server is overloaded, right? Because all of these videos, when you are moving in a clockwise direction, all of these videos will be stored in this server. Whereas this server has no load at all, right? So this uneven distribution makes it worse. Let's say this is our server 1, this is our server 2, this is our server 3. So uneven load distribution becomes a crucial issue in consistent hashing or circular hashing concept. In order to tackle this problem, what we will do, we will introduce a concept of virtual servers. Okay, we'll create virtual servers like this. Okay, and we'll place them randomly. We may create, let's say, 3 copies of virtual server v1 as virtual server s1. Okay, and we can place them across the ring wherever we want. Let's say we have created 2 copies of it, and this is, let's say, s1 underscore v1. Then we are creating, let's say, one more copy of this, and s3 is, let's say, placed here, and this is, let's say, s3 v1. So like this, what we are doing, we are creating virtual copies of the servers, right? Let me just move these things. So in this way, what will happen? Now what we are doing, we have virtual copies, right? We have virtual copies of the server in the hash ring. Now, using the same concepts of hashing and hashing the server IP and object keys, now we'll be distributing the load across multiple servers. Now when we will be calculating the corresponding server for these objects, right? These objects, you will find that, yeah, these videos has to be stored in S1. So you'll go and actually, let's say this is S1. So you will actually store this in the S1 server, because the address is S1v1, but this is the virtual address. We don't have a physical address like S1v1 as such. So you will utilize S1 for this S1v1. So finally that object will stay here. Okay. Similarly, and let's say this object, right? Earlier when S3 was not there, all of the video were going to S1 only, right? But now as soon as we introduce some concept of virtual server here, now this object, this pink object that you see here, that is now a part of S3. Let's say this is S3, right? Server 3. So that's how we introduce the concept of virtualization in the hash ring to do even load balancing or load distribution. And now more the number of the virtualized server in your hash ring, the more will be the even load distribution across multiple physical nodes. Okay, but how many virtual servers you should have, that depends on your application structure and your query and your architecture plan. You can have 2 to or 10 or 20 virtualization per node, right? Per server you can have 20 virtualization nodes across the circular hash space. But there is a trade-off definitely, because you will be storing the metadata, right, for each of these virtual server, because all of these virtual servers finally target to this single physical server. So it will definitely take a lot of space from your hash space, definitely, and you have to store the metadata repeatedly and redundantly in your hash space. So that's up to you. That's a trade-off you have to do definitely in order to accommodate for the even load distribution and have fault tolerance in your architecture. So you understood today, when someone comes and uploads his reels in this central server, that video is sent for caching to this S server, and inside this S server, let's say this is a distributed edge server. Okay, so this is a distributed edge server of this. Let's say this purple color server is actually a cluster of some distributed cache servers like this. The videos are actually cached in this distributed cache server using the concept of consistent hashing. Okay, and that's how you get to access the reels in a smooth and fast manner without any lag, and in a seamless manner you're able to access the reels on Instagram. So consistent hashing is a quite important concept in all of your content delivery network platforms. Almost all the content delivery platforms use this consistent hashing for minimal disruption when there is, let's say, server failure or they are scaling up the application. In all the cases, consistent hashing is able to handle those kind of scaling and downscaling and upscaling things with minimal disruption in the application and without disturbing the UX. Okay, so if you understood about the concept that we discussed in this video, that's the consistent hashing, which is one of the important system design algorithm that you need to learn. Okay, and if you like my content and like this video, please consider subscribing to my channel. I create this kind of real life use cases based on system designs. You can check out my playlist on system design use cases and basic concepts. You can click on the eye icon to explore those. So you'll definitely find them interesting and resourceful. So if you have any doubts about whatever we discussed in this video, put them in the comment section. I'll be definitely answer them. So thank you for watching this video, and I'll see you in the next one. Thank you.